If there is an R lies between y equals f of x and y equals g of x, where f is more than g, the area between the curve is the integral from a to b f of x minus g of x. In order to find the center of mass, we divide the interval AB into many subintervals. Each of the subintervals gives us a rectangular strip. Now, recall, if we only have f of x above the x-axis, the moment about the y-axis is the integral from a to b, x times f of x dx. The moment about the x-axis is the integral from a to b of 1/2 f of x squared dx. But this time we have two curves f above g. The area of the rectangle is now no longer f of x delta x. So the moment about the y-axis is the mass times the directed distance to the y-axis. But the mass is now density times the height. The height is now f of x minus g of x. The width is still delta x times the distance xi from the y-axis. The total moment is the sum, the density, xi, times f of xi minus g of xi, delta x. But this at n equal to infinity will give us the definite integral from a to b, delta x f of x minus g of x dx. Note that the rectangular strip now has a center of mass as xi bar, but the y bar is half of the distance from f to g, which is half of f of x minus g of x. And so the moment about the x-axis is the mass times the directed distance to the x-axis. Delta, the height is f of x minus g of x, the thickness is delta x. But the distance to the y-axis is now 1/2 f of x plus g of x. Simplifying this expression, f of x minus g of x times f of x plus g of x is the product of the conjugates. So we end up with f of x squared minus g of x squared. Take n go to infinity, we have the definite integral from a to b, 1/2, the density, f of x squared minus g of x squared. We can ignore the density if the density is constant or uniform. And so even though x bar equals the moment about the y-axis divided by the mass, once we ignore the density delta, we have the moment of y divided by the area to get x bar, and the moment about the x-axis divided by the area to get y bar.